Hi everyone. Today our plan is going to be, we're going to start section 5.3. And now hold on, guys. Ah! It's the scariest word in high school mathematics. Prove. Now calm down, all of you that are having post-traumatic stress memories from geometry. It's not the same. It's not two column. In all reality, this is not going to be appreciably different than what we've been doing in section 5.1. And in fact, in some ways, it's going to be easier than what we did in 5.1 because you'll know the answer that you need to end with. Okay? So we're really going to be doing the same things, except now we know where the ending is. So I want to start here with just a couple of strategies or guidelines to kind of help you guys get started. And then we're going to run through some examples with me. And then we'll run through some examples with random volunteers. Your favorite. Okay. So we'll start with just the first, these first 6 things are like guidelines or general strategies that would be helpful. So when doing any of these trigonometric identity proofs, you're only allowed to work on one side of the equation. Okay? You can't do things like cross multiply. You can't add something or subtract something from both sides. Those aren't allowed. You pick one side, and that's where you're going to live. Everybody's okay? To make a decision about which side you want to choose, there is no wrong choice. Okay? But many times, one choice is going to be, quote, harder than the other. In general, you want to choose the side that's more complicated than the other. In my experience, it's typically easier to like cancel things out and reduce things down and combine them together to get something simpler than take something simple and break it apart. That's usually a much harder mental process. It's kind of like walking uphill versus walking downhill. If you're going the canceling route, typically things like, it's kind of like walking downhill. You guys okay with that idea? So again, not a right or wrong choice, but you can make your life harder than maybe it needs to be with a poor choice. In the event that you're stuck and you're just like, I just don't have any idea what to do to proceed, writing everything in terms of sine and cosine is usually never a bad choice. Now, it might not be the most efficient choice, but it's typically not a bad one. Number 4 says combine fractions by getting a common denominator. If I see on one side of my identity like 2 fractions added together, and on the other side of the identity I see one thing, I know that at some point I'm going to have to add some fractions to get there. Or even if I see 2 things added together on one side and a single thing on the other side, I know I'm probably going to have to use an identity, convert them to fractions, add them together, and do some mumbo jumbo to end up on the other side. So again, common denominators, adding fractions is going to be a normal thing that we do while doing these proving these identities. Number 5 is that this difference of 2 squares that a squared minus b squared is equal to a plus b times a minus b happens all the time. Typically taking like an a plus b and multiplying like the top and bottom by like a minus b to create a difference of two squares is often really, really effective on these identities. Often it's the key to like unlocking to get to the next step, because the a squareds minus b squareds often fall into the form of one of our Pythagorean identities that allow you to like make a substitution and get rid of some addition and subtraction. And then my last item here says always be mindful of your target expression, what you're working towards. Keep your eye on where you're trying to get to. Oftentimes there's going to be clues about like, okay, what is the piece that I have to work on changing based on what I need the final answer to look like. It might tell us what to multiply the top and bottom of a fraction by. It might tell us what thing do I need to work on changing with an identity. It might tell us that like, oh, these fractions have to get a common denominator to get them together or something, because two things have to turn into one thing. You know, like these are all really helpful information, clues along the way. Your job is to put on like your deerstalker cap and turn into Sherlock Holmes and try to find the path from the start to the finish. Is everybody okay with this idea? Let's do some examples. Now, these first examples, I'm going to start by just kind of like talking through and taking some like voluntary volunteers to just give you a feel. And I'll do things wrong intentionally here and there to kind of illustrate points that I think are good things for you to have seen. Now, while working either in the notes or on the note sheet that we have that we'll look at in a second, what other piece should you have out on your desk? Nah, don't worry about the unit circle. The identity sheet that is on the other side is the unit circle. Get those identities out. You'll be looking at these while doing this. Quite helpful to you. If you've lost your identity sheet by now, number one, shame on you, but there are extras on top of the file cabinet if you need one. This is like the third one I think you've gotten loose.
Oh, it's not.
No?
No.
Okay. Just a second.
I'll give it back at the end.
Well, I'm just teasing you. Jack is trying to do a second homework assignment here instead of getting identities.
Oh, that's what I did.
Oops. All right. So I'm going to do like 4 examples here for you guys. We'll kind of talk through things as I go. I might ask for some volunteers on ideas of what to do as we get a little bit deeper in, but this is going to just be, shh. The goal here is just to try to build up some intuition for you guys, okay? So, first thing I want to do is I want to look and decide which side of the equation do I want to work. Do I want to work the left-hand side or the right-hand side? My advice in general is to choose the more complicated of the two. So, Mr. Kulik, what the heck do you mean by more complicated? Which is a fair question. When I look at the left-hand side, I see 2 things, right? When I look at the right-hand side, I see 1 thing. Now, I understand that right-hand side has 2 things multiplied together, but in terms, like in algebraic speak, this is like 1 term, this is like 1 term, this is like 1 term. What's more complicated, 2 terms or 1 term? 2 terms. I would start on the side with the addition. Everybody feel okay? All right. So I'm going to go, okay, so I'm going to start with tan x plus cotangent x. And I'm going to try to turn that into secant x times cosecant x. All right. So there's nothing algebraic I can do to add tangent and cotangent together, right? So I'm probably going to start with an identity. So if I go and I look at my identities for tangent, I can say tangent is equal to 1 over cotangent. I can say tangent is equal to sine over cosine. Or I can say tangent is equal to secant over cosecant. Seems like that choice might be the best one because my final answer has secants and cosecants in it. So let's do that. Now, just as a matter of style, when I work on these proving identity problems, typically I like to work vertically down my paper as opposed to horizontally. The simplify problems, like we've done in section 1, I like to do those horizontally. The identities I like to work vertically because it just allows me to kind of keep in mind that I'm always trying to get to a specific answer. Like I know what the answer is. I know where I'm trying to get to. So I've done that. I've used Q1 and Q2 to rewrite tangent and cotangent in terms of cosecants and secants. Seems to me that the next thing I'd want to do would be making a common denominator to add these two fractions together, right? Can anyone tell me what the common denominator would be between these two fractions? Secant times cosecant, right? Thanks, Golbs. So I'll take the first fraction, multiply it by secant over secant, and we'll multiply the second fraction by cosecant over cosecant. And the note I'll just make there is that we did a common denominator, right? All right, if I combine my like terms, secant times secant is secant squared. And cosecant times cosecant is cosecant squared. And then my denominator is secant times cosecant. So far, so good. So if I look now, okay, well, I can't combine secant squared and cosecant squared. Those don't add together. Maybe I go look at my identities. All right. If I look in the numerator, I have secant squared and cosecant squared. So maybe I'll look at the Pythagoreans.
P1.
Well, not P1. Right? Because I don't have sine squared or cosine squared in the problem anywhere.
Oh, yeah.
But maybe I could turn cosecant squared into 1 plus cotangent squared. But I'm not sure I want to really do that because I want to end up with secants and cosecants at the end.
Secant squared.
So, well, I could turn secant squared into tan squared plus 1. But again, that doesn't seem like that's helping me. At this point, I'm not really sure what to do. So at the beginning, we had a couple of different options, right? We chose to turn tangent into secant over cosecant. I might just start over and try making a different choice at the beginning. If I don't see where I'm going, this was on purpose. You'll do this. I want to show you that it's okay to do this. If I don't see where I'm going after a couple of steps here, it doesn't seem like I'm getting closer to my answer, it's okay to just be like, you know what, let me just try doing something different. So at the start, let's do, instead of changing, I'm still going to use Q1 and Q2, but I'm going to use this time, bless you.
Thank you.
Turn tangent into sine over cosine. And I'm going to turn cotangent into cosine over sine. And then I'm still going to make a common denominator. Just like before, the common denominator is going to be like just the two denominators multiplied together. And when I combine like terms here, we've done the same 3 steps. We've just used a different identity at the start, or a different version of the identity at the start. And now let's look at what we have here. Well, now I see something immediately that's going to be a good decision, right? What do you notice is going on?
Sin squared plus cosine squared.
Yeah,
P1.
that's P1. I know that that's 1, which is great because now I've gotten rid of all the addition and subtraction, right? Remember where we're trying to get to is secant times cosecant. There's no addition or subtraction there, right? So I've just made a really nice improvement, something that I didn't see an obvious way to do before with our first set of choices, right? That's what I've been trying to do, is get rid of the addition and subtraction so I can turn this all into a multiplication problem. That looks pretty good so far. I'm going to do my rewriting trick that we've done before, where I've sometimes taken a fraction and turned it into the product of 2 fractions. And hopefully at this point you kind of see where I'm going, right? I can use R4 and 5 to rewrite this as cosecant x times secant x, which is going to be the same thing as secant x times cosecant x, and I'm at the finish line. So at the end of my proofs, I draw that square and then I fill it in. That's just like the indicator that you finished your proof, is all that symbol means. You guys feel okay? Okay. So again, I did that in kind of a less than optimal way to show you guys that, like, if it doesn't look like you're making progress, it's okay to stop and try something else. Yeah. Sure.
Is that the answer?
Yeah.
Is that right?
No, the answer is the work. So like what I'm going to be looking for on the problem is you taking the left-hand side and showing me how I get to the right-hand side. Right? So your answer is the work, is the steps. We know the 2 things are equal. That's given to you at the beginning. The problem is showing how they're equal. Ms. Kilby, does that make sense?
Yeah.
Okay. All right. Let's do the next one. All right, so if I look at this one, We'll start the same way. Which side looks like the more complicated side? They seem the same, right? Fair enough. They're just one fraction each. I'm going to choose to work on this one. And this one can be a little bit puzzling on what to do at the start, right? If I look at this, the only trigs I have are cosine and sine. There's not an obvious identity to use for either of those. Those seem like, why would I want to turn cosine into 1 over secant or sine into 1 over cosecant when where I'm trying to go is just got sines and cosines in it to start with? Everybody agree? This is a great example of looking at where you want to get to as a helpful hint. If I look, the numerator of where I want to end has a 1 plus sign in it, right? The denominator of where I'm at has a 1 minus sign in it. Well, one way I can get the 1 plus sign into the numerator is to just multiply the top and bottom by 1 plus sign. And I feel even better about that because if I look at the denominator, that's that difference of 2 squares stuff going on there, which is usually a good thing to do. Is everybody okay with the reasoning there? So my numerator, I'm just going to write, I'm not going to multiply it out, but I am going to FOIL the denominator. Now, when I say FOIL, I'm not really going to be doing like multiplying the first, outer, inner, last. I know what the answer is going to be to that FOIL problem. I'm just using that factoring pattern, right? I had a plus b times a minus b. I know the result is going to be a squared minus b squared. Now, if you're not good with that, you go ahead and FOIL like the normal Algebra 2 way. You're going to be fine. I like just using the shortcut. I'm going to use the shortcut every time. You're welcome to do that as well. Unless you're like, yeah, that's not going to work well for me. Then don't do it. It's okay. All right. What do you notice now? So I have that 1 plus sign in my numerator, right? Somehow 1 minus sine squared, though, has to turn into cosine. Well, is there something that I can turn a 1 minus sine squared into something with cosines in it? P1, right. 1 minus sine squared is cosine squared. What do you guys see to do from here? Yeah, you can reduce. And you're left with exactly what we need, right? So we're done. It's cool. That one seemed a lot easier. Sometimes they're going to be, right? Sometimes it's just going to, you'll see what to do right away. And maybe you do a little bit of exploring, but after like 1 or 2 steps, you're like, I see the finish line from here. That's pretty normal. Like some of us will eventually get to the point where you can look at them and see all the way to the end without having to do any exploring. But, you know, after a step or two, we're at this, I would expect us after the homework assignment, if you can't see the end by 2 or 3 steps, probably start over and try something different. Or look for like a silly algebra mistake that you made, like you reduced something wrong or something. But that should be kind of the normal pattern on these. So maybe you're not sure how it's going to work at the start, but you're like, well, I have some good ideas of stuff that I can do right now. And after you do a couple of them, you're like, and now I start to see all the way to the finish line, right? That's usually, like at this stage of the game, you're hopefully able to see like, 2 or 3 steps ahead. All right, so if I look at this one, which side do you want to start with?
Left side.
Seems like the left side, right? That's what I would do too. What's the first thing we want to do on that left-hand side?
Distribute.
Yeah, and by distribute, you really mean FOIL.
Yeah.
Yeah. Again, if I look over here, I see no addition and subtraction. So now I need to get rid of that. I have addition and subtraction in 2 places. By foiling, though, I notice that's another difference of 2 squares. That's going to knock out the addition and subtraction down to 1 place. So if I look at the numerator, I have 1 minus cosine squared. Can I do something there to get rid of the addition and subtraction? P1 allows me to say that's sine squared. That's good. So we've gotten rid of all the addition and subtraction. Remember, we're trying to get down to this single tan squared. Right now we have division. Can I do something to change the division here? Q1. Yep, that just turns into tan squared, and then we're donezos. Oh. See, these aren't all so scary, right? Some of them are scarier than others, and once you've kind of picked up on the tricks, the usual set of tricks, they're usually pretty doable. Now, if you make some bad choices, you can take a problem that could be done in like 2 or 3 steps and turn into something that you took 10 steps to do. That's not uncommon, but the more of these you do, the more kind of patterns you end up seeing, and it's easier to kind of see your way to the finish line. All right, this is the last Mr. Kulik example before I start taking some not so voluntary volunteers. Which side do you think you want to start on? Bella says the right side, which seems like the more complicated side, right?
Yeah.
This is an example of one where I would violate the general rule to start with the more complicated side. Let me explain to you why. So when I look at this, well, actually, let's say this. Shh. So I see a cosine alpha over here, right? On the right side. And I see 5 cosine alphas there. So I know that this stuff, this trinomial, is going to be occupied by this sine squared and then the remaining 4 of those cosines, right? When I look at a trinomial like that, what do you think when you see a trinomial? You should be thinking about factoring, right? Now, so to go this way, we're going to end up having to factor. So what's the opposite of factoring? Well, not quite distributing, but FOIL. Which one would you rather have to do, factor or FOIL? You guys are crazy. FOILing is way easier than factoring.
Yeah.
So I'm going to pick to use this side because I would rather have to FOIL than have to factor. Now, it's not wrong to take the other side. It's still eminently doable, but the factoring is always going to be harder than the FOILing. All right. You guys feel okay with what I saw there to convince myself to take the less complicated side this time? All right. Yes, sir. Yes, sir. So I'm going to start by just doing a little rearranging. So I'm going to start by rewriting this cosine to the fifth as cosine to the fourth times cosine, because I have that part of the final answer already set. That cosine alpha at the end is the same as this cosine alpha. That's going to just ride with me to the finish line. I'm never coming back and messing with that guy again. Sure. Everybody feel okay there? So if I look at what's remaining here on the finish side, it's all sines, right? Everybody see that? In the trinomial, it's all sines. Oops, that's supposed to be sine squared. So I have sines here. I'm not going to mess with those because they're already in sines. But this, that's what I'm going to try to turn into sines. Everybody okay with that plan? Good with the reasoning? At what I'm looking at to make this decision, to tell me what to do next. Now, if I look at my identity sheet, I don't have any cosine to the fourths. But if I rewrite this again as cosine squared times cosine squared, now I'm good to go, right? I can use P1, well, twice, to rewrite cosine squared as 1 minus sine squared, and then 1 minus sine squared again. Does everybody feel good so far? All right. So if I look now, those three things have to give me that trinomial. Everybody's okay? Well, I just start multiplying them out, right? If I have three things multiplied together, if I need to turn them into one thing, I just need to multiply them out. So I will choose to start by doing the foiling first. Typically, I'd rather foil first and distribute second. I think it's less likely to make an algebra mistake. So 1 times 1 is 1. 1 times negative sine squared is negative sine squared. Negative sine squared times 1 is negative sine squared. And negative sine squared times negative sine squared is positive sine to the fourth. Remember that when we multiply exponents, we add the exponents, right? So far, so good? If I combine my like terms, I notice that I have a minus sine squared and another minus sine squared. So those can come together into minus or 2 negative sine squareds. And now I'm just going to distribute that sine squared through. Sine squared times 1 is sine squared. Sine squared times negative 2 sine squared is negative 2 sine to the fourth. And then sine squared plus sine to the fourth, or times sine to the fourth, is sine to the sixth. And that is exactly what we had in the previous, or on the right side, or the finish side. Yes, sir. Yeah. Tia, what's up? When somebody gets back, you can go. He's the third one out, so it's a race. Who do you think's going to be back first? Jack, Mira, or Aiden?
Wilhelm.
Will Hannah's absent, so he's definitely going to be the last one back.
Oh, looks like it's a lost cause.
All right. Let's go and look at the note sheet now. So it's time for some not so random volunteers, or I'm sorry, some random not so volunteers. Right? Not so voluntary volunteering. So I'm going to call on some random people to help walk me through what we need to do. Ashton, you are first up. So let's take a look at the first problem here. When I look at this, I notice that there's no trigs in here, right? So it's going to be all algebra to finish this guy off. What do you think? What do you think a first good algebraic step would be, or which side should we work on? Yeah, I just don't have to like. They'd be a madman to want to start with the right side, right? All right. So let's start on the left side. What do you want to do?
Simplify the two fractions, like reduce, or like make them small.
Great. How are we going to do that?
You can cancel out a lot.
By doing what?
Subtract. Right?
But this is an addition and subtraction problem, and this is an addition and subtraction problem.
Okay.
Now, they might be able to reduce,
Yeah.
but you need to do something first to see if they are reducible. Starts with an F. Factor. Factor is right. So, what part can factor, the numerator or the denominator? Okay. Should be no surprise there, given that it's the only one with a squared in it, right? Ugh. Stupid thing. Okay. How does x squared minus 1 factor? So hopefully what you see is that looks like that difference of two squares factoring pattern, right?
Yeah.
So x squared minus 1 factors to, you said x.
Minus, oh, so
X plus 1.
x plus 1.
X plus 1,
Yeah.
right? A plus b.
Yeah.
So we do that for both of them. And then what do you notice now?
You can get rid of, on the left side, you can get rid of x minus,
Mm-hmm.
and then the x plus.
Okay. So we'd have, this is all that's left, right?
Yeah.
Unfortunately, that's not correct. Now, I've made a mistake intentionally here because I would guess that 80% or more of us would make this same mistake, and I want to point this out because it's probably a trick that I would try to pull again.
Okay.
And it's a good thing to illustrate here. So I've intentionally made a mistake in going from this step to this step on how I've written here. The canceling is fine.
You need the points.
Yeah, great. So that's right. Now the first set of parentheses, do we really need those? No, because there's nothing in front of them, right? The second set of parentheses we do need to have,
Yeah.
because we need to make sure we distribute the negative. Everybody's okay there?
Yeah. Yeah.
Yeah, that looks good, right? What do you notice can happen?
Like,
Yeah, so x and negative x, that gives us 0. 1 plus 1 is 2. That's where we're trying to get to. We're done. Notice that I wrote this horizontally this time just because of the space constraints. If I had like a free sheet of paper, I'd write it vertically, but it is what it is. Space is the space. What do you guys think? Is that okay? So again, we like factor, reduced, and combine like terms or something. The next one is actually one we did already in the notes, so we'll skip that. Going on to the back page then. My next not so voluntary volunteer is Tommy.
Okay.
Yeah, okay. All right, which side do you think we should work? Left or right?
Left.
I agree. What do you want to do first on that left side?
Combine like terms, so multiply.
What do you mean by?
Like, so we can get the same denominator.
Oh, okay, make a common denominator.
Yeah.
Great. What should I multiply the first fraction by then?
SCC plus 1.
Great. And what about the second fraction?
SCC minus 1.
Great. Yeah, we just combine like terms or whatever here. So we're going to have secant x plus 1 times 1 is just that. Oops, forgot my plus sign there. And then secant minus 1 times 1 is just secant minus 1. And my denominator, let's FOIL that out at the same time, eh? So far, so good?
Yeah.
Okay, what do you notice happens in the numerator? Go ahead.
It becomes SCC squared.
Not SEC squared.
Or
2.
SCC,
Yeah, 2 secant. And if I pause right here, I observe that, hey, there's the 2 that I'm looking for. That's great. I love to see that popping up. I'm pretty confident that I'm going the right way when I see stuff like that. What can I do with that denominator?
Is it boiling or vacuum? Split up.
Well, I wouldn't do either. It's factoring.
What should I look at my paper and find?
Yeah, there might be an identity there. Often after we've done a difference of 2 squares, there's an identity to use.
Oh, it's tangent.
Tangent squared. Yeah, that's P3. Mm-hmm. Okay. So let's go back and look at where we need to get to again. Maybe there's a clue of what to do next. So let's see. I see I have a cotangent here. Remind me, what are the different ways I can write cotangent? If I look at my identity sheet.
Cotangent, is it 1 over tangent?
1 over tangent, and then what else?
Cosine over sine.
And what else?
CSE over secant.
Okay, so cosecant over secant. Now, the only one that I have in the right place is the tangent in the denominator, right?
Yeah.
So I would probably do a little rewriting now, and I would write 2, and I'll take one of those tangents from the denominator and put it over 1. And then I'll leave the other one there. Because I recognize this is the same thing as cotangent, right? So I'm happy about that. That means that this rest of this stuff needs to somehow simplify down to cosecant.
Oh, okay.
Does that feel doable so far?
Yeah.
Okay. So we have that step. What are we going to do to deal with secant over tangent? Can we...
Secant is 1 over cosine, right?
Mm-hmm.
And then the inverse of tangent is cosine over sine, right?
Yes. Can I pose to you an easier way to think about this?
Yeah.
So look at the identities for secant and tangent and see if either of them have a cosecant in it. So if I look at Q1,
Yeah.
tangent is secant over cosecant.
Yeah.
Why am I looking for a cosecant? Because I need to have one in my final answer. So that's the identity that I would choose to do here. So I'm going to have like secant over, where was it? Secant over cosecant. Now to see this simplify, I'm going to think about the numerator as like secant over 1. And if I divide fractions, I make a reciprocal.
Yeah. And then they just cancel.
Yeah. And there's my finish line.
Look at that, I can still do it.
Yep. Not bad. So again, like going back, looking at where you're trying to get to, often has a lot of clues as to like what to do next. Like which identity would I want to use? I have a lot of options here. Like which one would I want? The end, knowing the end point really helps you choose.
Yeah.
Colbs.
Where'd you get the cotangent from?
So the 1 over tangent on the previous step. R6 makes that cotangent.
Oh.
Is that cool? All right, let's see. Good job, Tommy. I asked you a lot from you there on that one. Jack Hallman, you're helping me with the last one.
Mr. Face, rest you don't need to wait for someone to come back.
No, man, you're good.
All right, thank you.
So we're skipping the middle because we did that already in the example. We're just looking at this last guy. All right, which side do you want to start with there, Jack? Going to start on the right. You're the only one that's chosen that. I think this will be the easier route, though. I've done this 3 times today. Nobody else wanted to start on the right-hand side. I think that'll be easier. What do you want to do on the right-hand side?
Would I factor, or not factor out, but would I distribute it?
Yeah, we can do that. Okay. Now what you want to do?
Would I use Pythagorean?
Well, you don't have anything squared, so I wouldn't do that.
Is that co-function or no?
Well, if you're not sure, what's usually never a terrible idea is just to rewrite everything in terms of sine and cosine.
So I just use the,
I'd use like Q1, yep, and the reciprocals. And then Q2 and the Q1.
and just cancel some.
Yeah, a lot of stuff to cancel, right? Boom, 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 boom. So we have left 1 over sine u minus 1.
Okay.
Yeah, it doesn't seem like maybe we went a little bit too far here, huh? Let's take a look here. What can we do? Okay. So let's make a common denominator. So I'll multiply 1 just by sine u over sine u. Which is probably a good idea because the left-hand side is 1 fraction, right? So getting the thing into a fraction is going to be helpful to us. And then I see half of a difference of 2 squares. So let's do that. If I look at the numerator, that's cosine squared. Okay. And if I then, I got to turn this cosine, if I look at the end where I'm trying to get to, this cosine squared's got to turn into cotangent squared, right? If I look at cotangent squared, if I look at Q2, it's the same thing as cosine squared over sine squared. So I'm just going to force a sine 1 over sine squared in there. So the numerator then will be cosine squared over sine squared. The denominator, I'm going to be a little sneaky here. So I'm really going to think about this one as 1 over sine times 1 over sine. Because I'm going to think about sending one of them there to give me 1, and the other one I'm going to distribute into here. So there's the 1, and then I have a 1 over sine u, and then plus a 1. Now, cosine squared over sine squared we know is cotangent squared. Check. That's what we need on top. 1 over sine is cosecant. And that's what I need on the bottom. So that's going to be my finish line there. I suspect here, Jack, if we'd gone back, I want to look at what would have happened. I think we might have made a poor choice right from jump. What happens if we would have turned if we did that at jump, I think we would have been in better shape. And then if you multiply the top and bottom by 1 plus cosine and kind of follow the same steps, I think you're going to be in better shape. I think it would have been a directer route to get there. But what we did worked. Now it got tricky towards the end, but this was going to be kind of tricky regardless. All right, what do you guys feel? Bah? Nah? Like I need some practice? Yep, great. So for you guys' homework assignment, I'd like you to work on 47 through 54. That's 8 problems.
Did you finish this sheet?
Finish this sheet, the note sheet.
Yeah.
The only ones we skipped were the ones we already did as example problems in the notes. So you can if you want to, but you don't, I mean, we already did them. It's good practice though, if you're not looking at what we did before to try them. But you don't need to. It's not to turn in, it was just something to have in front of you to make it a, I don't know, slightly more interactive. Sure. Any questions for me?